Okay, this is our first lesson on Unit 16. 16 is all about being able to sketch given a function, sketch an accurate picture of the function or an accurate graph of the function. So in boxes A and B here, we're going to look at intervals of increase and decrease, and we're going to recap how you find horizontal and vertical asymptotes. So let's just jump in here with an example. If we've got a function here, f at x equals x squared over x squared minus 4, we're going to want to be able to find the intervals of increase and decrease. To do that, we're going to need to be able to find the local maxima and minimum points, and then we're going to move on and find the asymptotes. So if we're looking for intervals of increase and decrease, what we want to do first is we want to find the critical numbers. Because the critical numbers were the points where it was possible for our curve to change from increasing to decreasing or from decreasing to increasing. And our critical numbers occurred where our derivative was equal to 0 or our derivative did not exist. Okay? We haven't talked too much about this case where our derivative did not exist because up until now we've been dealing with mainly polynomial functions. But if you look at this f at x here, this is a rational function. We've got something in the numerator and the denominator. So it's going to be, we're going to run into a lot of cases where our first derivative does not exist, and we have to take that into account. So let's start here by finding our critical numbers. So we need our derivative. So f primed at x. And we can just use the quotient rule here. So we can do 2x times x squared minus 4 minus x squared times the derivative of what's on the bottom, which is 2x, all divided by x squared minus 4 squared. And we're going to want to simplify the numerator here. So we get expanding, we get 2x cubed minus 8x minus 2x cubed, and denominator stays the same. And luckily for us here, these terms cancel out, and we're left with a fairly simple numerator, and this term down here in the denominator. So there's our first derivative. So to find our critical numbers, we're interested in where our derivative equals 0 and where our derivative does not exist. So if we're looking for where the derivative equals 0, we're interested in where the numerator is equal to 0. So numerator equals 0. So we'll set our numerator, 8x equals to 0. And, of course, when we solve this, x equals 0 is one of our critical numbers. But what about where our derivative does not exist? Well, our derivative is not going to exist at points where our denominator is equal to 0. So let's set our denominator here equal to 0. X squared minus 4 all squared equals 0. And let's solve. So we can take the square root of both sides to get x squared minus 4 equals 0. And we can factor the left side as a difference of squares. X minus 2, x plus 2 is going to equal to 0. So here we have two critical numbers, x equals positive and negative 2. What we want to do with these now is we want to find the intervals where our function is increasing and where it is decreasing. So to do that, we're going to set up our interval table, just like we did when we were applying the first derivative test. And we're going to use our critical numbers here to define our intervals. So let's just say we use these guys to define our intervals. And what we're checking is the sign of the first derivative. So let's set up our table here on the next page here. So we're going to have 4 intervals because we had 3 critical numbers. So we're going to have -infinity to -2, -2 to 0, 0 to +2, and 2 to +infinity. And we're checking the sign of the first derivative. So we want all of those terms that appear in the first derivative listed down the side. So we had a -8x in our numerator, and we had an x squared minus 4 squared in our denominator. And what we want to find out is, in total, what is the sign of our second derivative? So I'm just going to draw some little lines here for our table. Another one here at the beginning. Okay, so -8x. Let's see. It's going to be opposite in sign to whatever the sign of x is. So where x is negative, this is going to be positive and positive, and negative and negative. X squared minus 4 all squared. Well, if we're squaring everything, it's got to be positive everywhere. So totaling these up, we get positive, positive, negative, negative. Okay. So what does this tell us about our function f at x? Well, if the slope of the tangent, or the derivative, is positive, that means the line, our tangent must be going up like that. So our function must be increasing. So in these 2 intervals, our function is increasing. And in these 2 intervals, our function is decreasing. So there, we've identified the intervals of increase and decrease. Do we have any local maxima or minima based on this interval table here? Yeah, we have 1. Where is it?
0.
Yeah, at x equals 0. So this is is it a local max or a local min? Yeah. And we know that this is a local maximum because we go from increasing to decreasing. So local max at x equals 0. And of course, we could sub x equals to 0 back into our function, and we get that f at 0 is 0. So that would be the point 0, 0. Okay. So that gives us our intervals of increase and decrease and our local max and min. The other thing we were asked for were our asymptotes. So let's just refresh our memory on how you find asymptotes. Now, if we're doing the asymptotes, remember that you have to go back to the original function. So we've been working with the derivative. Let's just write out what the original function was, mainly so I know what it is. You guys have it written down on your page, but okay. There's our function. Do you guys recall how you figure out where a vertical asymptote is?
You set the top equal to 0.
Yes. So it occurs where denominator equals 0. Sorry. You said the top. Yeah, you meant the bottom, right? And I wrote denominator. Yeah, denominator equals 0. Yeah, so it's where the denominator equals 0, because those are the points where our function is not going to be defined. So in this case, our function is x squared. Okay, so we want to set x squared minus 4 equal to 0, and we want to solve for x. So again, we've already done this factoring. Okay, and we get 2 solutions, x equals -2 and x equals +2. So those two equations would represent our vertical asymptotes. Now, horizontal asymptotes. The method that you were taught to do this depends on who your teacher was.
So we just take like x squared and we like divide everything by.
Yeah. But you had Mr. Potvin, right? Yeah. If you didn't have Mr. Potvin, you learned a different method. Okay? So the method that Mr. Potvin teaches, he teaches because he knows that you're going to be doing this when you get to calculus. So it's the method that I'm going to use. I don't care what method you use. Okay? If you have a mathematically valid way of finding horizontal asymptotes, use it. Everybody's happy. Okay? Here's the method that I like, though. What is a horizontal asymptote? Okay? It tells you the behavior of your function as x goes to very, very large or very, very small values. So as x goes to either positive or negative infinity. Okay, so way, way, way out far from the origin, from 0. So one method we can use to do this is we can divide every term in our function by the highest power of x. The highest power of x that you see in the function, and then take the limit. Okay? Take the limit as x goes to positive or negative infinity. So what's that going to look like in this case? Well, our function is x squared divided by x squared minus 4. So our highest power of x is x squared. So what we want to do is we want to take the limit as x goes to positive or negative infinity of, in our numerator, we have x squared divided by x squared. So we had x squared originally, divide by the highest power of x. In the denominator, we're going to divide each of those two terms by x squared as well. So x squared divided by x squared, 4 divided by x squared. And then we can simplify this. This is going to be, again, the limit as x goes to positive, negative, infinity. X squared over x squared is just 1. X squared over x squared is 1. And we can't really do anything with the 4 over x squared. And the only thing that you have to know about taking this limit is that, I'll just write limits over here, something like 1 over x goes to 0. Because you've got 1, you're dividing it by something that is either, well, it's a very, very large number, either positive or negative. So if you take 1, divide it by something that is massive, it gets really small, close to 0. Same thing with a term like 1 over x squared. Same thing with a term like 1 over x cubed. So anywhere where I see something like a number over x squared, I can replace it with 0. And that's right there, as I evaluate this limit. Okay. So what this is going to be equal to is, I'm left with just 1 over 1, or just 1. So my horizontal asymptote is y equals 1.